Hi guys, we're going to start off this week with a little bit of a review of the relationship between rho, which is our charge density, V, our electric potential, and E, the vector electric field. And our learning objective is basically to kind of review this important figure in the book, 2.3.5. This first slide, I didn't want to do it in real time because it's kind of busy, but this is just a kind of graphic that I thought would be useful for understanding, again, everything kind of that we've done so far, okay, with all the different equations and ways to calculate things like fields. So I want to start in here with what I've drawn, okay, and what I've drawn here is just an object that is charged, okay. In this case, I kept it simple. It's a sphere. Don't really know what the charge density of the sphere is, but it's not 0. Okay, because the charge density of this sphere is not 0, okay, I know that the divergence is also not 0. And in fact, I can write exactly what that's equal to. Let me write it here. Rho over epsilon naught. Okay, and if you guys remember this idea of divergence, it's kind of like a flux over a volume, except for we're going to take that volume down to 0 to a point. With electric field, you could think about it as, is there a source of electric field there? Is there a source of electric field lines? Well, there's only a source when you actually have charge present. So in this figure, the only place where there's a source of electric field, a source of divergence, is actually in and on this charged object where the charge density is not equal to 0. Okay, if I go out here, outside of that charged object, even though there is an electric field, which I've depicted here with the red arrows, even though there's electric field, there is no charge density outside of that charged object. If there's no charge, then I know that there is no divergence, okay? So I know that del dot E is going to be equal to 0. Okay, there's another equation that we're given that relates the potential directly to the charge density, and that's this one here. So we're replacing the vector electric field here with the gradient of the potential, and that gives you this is called the Laplacian, if you guys remember, the Laplacian of the potential. That's also equal to something that looks like the charge density over epsilon naught. There's just a negative sign in there. So if we're outside of the object where the charge density is, this is also equal to 0. Okay, let's keep cruising along here. This next line, I point out that the curl of the electric field is 0 everywhere, okay? And that is just a fact. If you are in a static electric field, which means it's an electric field generated by a static charge distribution, charges that aren't moving, it's not going to have any curl. Okay, if I look here at, let's just look generally at the field here. Okay, so I've depicted the electric field with these red lines that point radially away from this sphere. In this case, the sphere, right, if I'm outside of it, we've learned that if you're outside of a spherically symmetric charge distribution, it actually looks like a point charge from the outside. So the electric field lines look like just what you'd expect for a point charge. These electric field lines, if they're drawn nicely at even intervals, okay, where they are more densely packed, that indicates the electric field is stronger. Where they are further away, that indicates the electric field is weaker. A lot of you guys are getting quite good at thinking about flux in terms of thinking about how these electric field lines intercept surfaces, come in and out of surfaces. That's fine as long as the electric field lines are drawn well. Okay. In gray here, I have the equipotential lines. Okay. These equipotential lines are lines where the voltage has a constant value. Okay. So you can almost think about a figure like this, like a topo map. Okay, so all of these lines represent a constant voltage. If I happen to have drawn them at even intervals, so say each of these lines is 5 volts apart from one another, okay, then you can look at them like topo lines where the lines are closer together. That indicates a steeper slope, okay, and the steeper slope corresponds to the strength of the electric field. So if these equipotential lines are drawn at even intervals where they're closer together, you're going to get a stronger electric field. And when they're further apart, which is indicating a more gradual change in potential or a more gradual slope, you're going to get a weaker electric field. Potential is the integral of the electric field, a line. So basically I do a line integral of the electric field along some path, okay? So it's kind of like what you do for work. If you remember when you're calculating work, you were doing the integral, or basically how much force was applied over some displacement. Here, it's like, all right, how much electric field was experienced over some displacement. To make this really clear, we're usually going to do this integral from some reference point, maybe infinity, or somewhere where we've defined is equal to 0, okay? And we're going to do that to some point r. Okay, so that will give you the voltage at some particular point. Okay, so you got to choose what line you do this integral from. If you do it from infinity, where we usually choose the voltage is equal to 0 to r, you'll end up getting the voltage at a particular point. Okay, but like, so here we've got a sphere, and I can think about, all right, what is one way I could calculate the electric field from this kind of spherical charge distribution or any other continuous charge distribution? Well, in order to do that, I want to think about breaking the sphere into little chunks of charge. And then I'm going to integrate, which is, remember, the same thing as doing a sum, but the things you're summing over have been shrunk to being infinitesimally small. I'm going to sum the electric field and the potential from those little chunks of charge. Okay, so when I integrate over this, basically you can think about it as putting into tiny little chunks with their own little charge. I'm going to treat them like point charges, but I'm going to go around and I'm going to sum the effects of all those little point charges up at a particular point in space. Okay, so we did quite a few of these. We set it up. This was kind of a challenging thing. Okay, but in order to do that, you just have to solve these integrals, and that starts with, right, defining your points where you're evaluating, well, first drawing a picture, but then you want to choose where you're evaluating the electric field. You want to draw a little sample point in your object in order to define what this separation vector is and what r hat's going to look like. And then you got to do the integral. And oftentimes these integrals are hard enough that you need to do them in something like Mathematica, okay? But remember, this is going to give you a vector electric field, so it's going to have 3 components in the x, y, z direction, or if you choose some other coordinate system, it could be in the r and theta and phi direction. Voltage is nice because you don't have components to this integral, okay? Once you solve this integral, you can take the gradient of the voltage to get those 3 components of the electric field. All right, another way to solve these kinds of problems, and an easier way if you have nice symmetry, which I would in this particular problem, is to draw what's called a Gaussian surface. So for this particular figure, it would make sense to have a spherical Gaussian surface because this electric field generated from this charge distribution has spherical symmetry, which basically means I could rotate it around like a ball, and I wouldn't tell from the electric field that it was rotating because it has symmetry in all those directions. Okay, so if I can define a nice Gaussian surface where basically the electric field is constant at the surface, okay, and also perpendicular or normal to my Gaussian surface, then I can calculate the flux through that Gaussian surface, and it's going to be equal to the amount of charge enclosed divided by epsilon naught. Okay, and I might have to do an integral or something kind of thoughtful about the enclosed charge, but if it's a problem that makes sense to apply Gauss's law to, this integral should be really easy to do, okay? If it's not easy to do, you've either set it up wrong or it wasn't a problem that applies itself well to Gauss's law. All right, the last thing that I wanted to talk about in this figure, this busy figure, okay, is this idea here. So now I've got a bigger 3-dimensional charge density. It's got some amount of charge per unit volume, okay? If I shrink the volume down to 0, what I'm doing is I'm making this a point charge, which is what we started with when we were thinking about Coulomb's law, okay? If the sphere is a point charge, then I have to describe this rho as some amount of charge, however much charge that point charge has, times our Dirac delta function. Okay, so this basically shows that if I shrink this down to 0, right, this is going to go to infinity when r equals 0, but it's going to be equal to 0 everywhere else. But if I integrate over this charge density over the volume, I get what I expect to get, which is the total amount of charge in my point charge, okay? So this is a mathy tool that helps the mathematics here work out, despite the fact that for a point charge, right, this rho goes to infinity right at the point. All right, so I'm just going to leave that there. Again, this is a really busy figure. If you guys want, you could pause the video a little bit and check this figure out, copy it down if you want to. But I like kind of having these kind of summary figures in my notes because it helps me pull everything together that I've learned so far. And what I want to talk about next is how to find the electric field of an object. And I'm going to talk about these methods from the easiest to the hardest way, okay? So if there is a good symmetric field, okay, then the easiest, and by the way, symmetric, it could be a spherically symmetric, it could be cylindrically symmetric, it could be planar, okay, that would be like a sheet of charge. If this is true, then you can find E, okay, with Gauss's law. This is by far the easiest way, the fastest way to do it. Okay, Gauss's law, of course, says that if you take the surface integral, right, and this is a closed surface, so you got to go all the way around a closed surface of the electric field, then that's going to be equal to the enclosed charge over epsilon naught. Okay, if you do it right, okay, the integral should be crazy easy, okay, like real easy, don't have to do anything hard at all, okay? If you have more than one charged object, okay, you can use Gauss's law to find the electric field from each object separately and then add them together. Which is basically using superposition, right? The superposition principle of electric fields. Okay. The last little note I wanted to make on this is the enclosed charge, it might be really obvious, it might be really easy, you might just have a few point charges in there, but it also might require, like it did in the homework, an integral or just some clever thinking, okay? How much of a certain type of charge density is enclosed. So that's not necessarily a given. Sometimes figuring out that can be the harder part of using Gauss's law. Okay, but if you can use Gauss's law, if you have a nice symmetric field, this is the easiest way to find the electric field. You're going to just find the magnitude, of course, but then if you do have a symmetric field, you should be able to reason what the direction of it is. Okay, either radial outward, up, down, something like that. Okay, So the next easiest way, if you can't use Gauss's law, is to find V first. Okay, and you could do that using the integral I talked about on the last slide. And then you could calculate the electric field from the negative gradient of that potential. Okay, why is this easier? Well, I said it a couple of times already, but V is a scalar. Okay, so you don't have to worry about vector components, which means basically you only have to do one integral instead of three. Okay, and in general, just doing this integral, which looks like 1 over 4 pi epsilon naught rho over this separation vector, okay, d tau is easier because you don't have that r hat in there. Okay, you have a little bit less to do in terms of the geometry of it. Okay, but still not necessarily easy, which means you still might need to either look it up in a table or use Mathematica or be really, really good at calculus. All right. The least attractive way, or the most challenging way to find the electric field is what we started with, okay? And that would be the straight up find E from this integral here, okay, which you guys should all be able to do and can do, okay? It's just not the easiest way. But we did some good practice with this. Let's see. Okay, this is not the easiest way. Okay, unless you are summing E from point charges, which in that case, you don't actually have to take the integral. You can just use the electric field equation that looks a lot like Coulomb's law, okay, and just do that vector sum. That being said, even though it's not the easiest way, you should still know how to do it. Okay, all of this, everything we've done so far in the class is really based on just a couple of things. The one is Coulomb's law, right, which gives us the force felt by a charge in an electric field. Okay, so that looked like that, okay, where we could say the big Q is a test charge, okay, and our little q is a source charge. If I define them that way, then the electric field, if you guys remember, is just defined as that force divided by the test charge. Okay, so it's this thing that we can define where you don't actually need to have a charge in the electric field to know what the electric field is, but you would need two charges to measure an electric force. Okay, and then this other principle, what we've done is based on this other principle that if you have a bunch of charges, then F and E is superimposed. Okay, which basically says you just have to sum up the electric force or the E field from those individual charges together. Okay, the last thing I want to do in this lecture is just go over that triangle that shows you how everything is related, okay? So this is just, again, it's a helpful thing to have in your notes. It's got all the equations in it, and it helps you see how you can calculate one of these components from the other ones, okay? So if you knew, for example, the charge density, you could find the voltage, or if you knew the electric field, you could find the potential. Okay, so let's just go ahead and write the components first. So that's the charge density. There's our potential. Okay, this is the only vector in the game, which is the electric field. Okay, the first thing I'm going to draw here is just what we started with, which is those longer integrals. So if I know the charge density, which basically someone's like, hey, you've got a uniformly charged sphere, or you've got a spherical shell with some charge density, or you've got a line with a charge density. Okay, that means you're starting with the charge density, and you could calculate the electric field directly from it using the integral that I just wrote down on the last slide. Okay, and again, some of these integrals, it's important when we're kind of writing them shorthand, right? I'm not writing the R, but that rho could depend on R or XYZ, okay? But I can calculate it directly from that integral. If instead I wanted to calculate the voltage, the integral looks similar, but it's a little different, okay? Now I'm just going to divide it by the separation vector because voltage is a scalar. There is no R hat in here. R hat is what turns this particular integral into a vector. I don't have an R hat here. Okay, so integration is a little bit easier. Okay, once I have those, say if I know instead the voltage and the electric field, or one or the other, then I can calculate one from the other. In fact, the voltage is basically defined to be the negative gradient, the negative gradient of the voltage is the electric field. And then this is how we define the voltage as being this thing that's equal to the negative of a line integral along a path of the electric field. Okay, so I can calculate one of these from the other using either of these equations. Okay, and then the last little bit is kind of closing this off. These ones are used a little bit less frequently, okay, but just with some math substitution based on how we define the voltage, I know that if I take the Laplacian, or essentially a second derivative, a second three-dimensional derivative of the potential, I'm going to get the negative charge density over epsilon naught. That's useful, okay, if I just want to calculate the charge density directly from the potential, okay, and then if I instead wanted to calculate the charge density directly from the electric field, I also have some options there, okay. In that case, I'm going to take the divergence of the electric field, which is going to be 0 if there's no charge present, no charge density, but if it's not 0, that means I'm in a object that has some charge on it, okay, and the divergence is going to be that charge density divided by epsilon naught. Okay, and the last little bit is I always know for an electric field, a static electric field, okay, we'll see this is not true once we have moving charges, but for electrostatics, the curl of the electric field is always equal to 0.